In this video, we're going to talk about section 1.2, displaying quantitative data with graphs. So moving on from categorical data graphs to more the quantitative data with numbers, how to appropriately show them to other people um, to influence them to make decisions. And we're going to talk about many different types of plots and graphs today. First, I can make and interpret dot plots and stem plots of quantitative data. Stem plots and dot plots, something you most likely have done before, but if you haven't, this is a good review. Or if you have, it's a good review. If you haven't, it's pretty basic in terms of how to order numbers. But if you have never seen it before, it might be difficult to actually go ahead and read from it. So first, stem plots. Stem plots are going to be separating each observation into a stem consisting of all but the final rightmost digit and a leaf. So the other name for this is a stem and leaf plot, or just stem plot. That leaf is going to be the final digits. Stems may have as many digits as needed, but each leaf can contain only a single digit. It's very important that each leaf contain only one single digit, because we're going to be putting a bunch of leaves next to each other, and there's more than one digit, you can't tell them apart. So each leaf has to have one digit. You're going to write the stems in a vertical column. And you're going to have the smallest at the top, draw a vertical line at the right of the column. So smallest at the top, biggest at the bottom. Write each leaf in the row to the right of its stem in increasing order. Increasing order. So you're going to go from the towards the away from the stem. You're going to increase the number. So in this example here, we have a table. It's got the country, and then female, male percent, country, and then female, male percent. So it's essentially a list of countries with the percentage and for males and females of literacy in Islamic countries. It's just two columns here, or two lists, kind of put next to each other. You're going to construct a stem plot for the percent of literate females. Describe what you see. So if you look at this list here, literate females, we're going to just focus on the female column. So I'm going to go ahead and cross out the male ones so we don't accidentally use them. So now we have two columns here of female percent literacy for each of these Islamic countries. We have a total of, it looks like 4, 9, and then 8, 17 countries or data points to look at. So we need to put those in a stem and leaf plot or a stem plot. I'm going to make my column first. Your left side of your stem plot are going to be your stems. So look for the lowest number in the 10 spot, because these are mostly two-digit numbers. So 60, 31. 31 seems to be the lowest so far, looking down. Go down this list here. 38, also pretty low. 29. 29 is the lowest number I found. So I'm going to put 2 here and then 9 to signal that's the one number that starts with 20, the lowest number. Then I'm going to go and look through the rest of the numbers here, and I see that I go all the way up to 99. So I got to make a stem for 2, 3, 4, 5, 6, 7, 8, and then 9. I don't have to make a stem for 10 because there's no number in the hundreds for the females. But I do have a Uzbekistan here, this digit or this data point or data value, 99. It starts with a 9, so I have to include that one. All right, so after 29, the next highest one we're looking for, we got 31 for Bangladesh, and then 38, and then I think there's only 2 in the 30s, so 31 and 38. So 31 and 38 are going to look like this. And go ahead and cross those off your list so you don't have to worry about them again. Same with Yemen here. You'll notice that when you make the list, when I make the list for you for the first time here, I'm lining up my data point values in columns. So I'll try and showcase that right now. Like, that's going to be what the first number, then it's going to be the second number, then the third number, and then forth. These highlighted marks you're not going to see on your paper, but you have to kind of visually do it for everyone because otherwise it's hard to look at the data set. If you kind of smush a bunch of leaves together, it may look like there's less amount of data than there actually is. In the 40s, I have 46 for Egypt, and that is it. Okay. So I'm going to cross out Egypt. 50s. I have nothing in the 50s, nothing in the 50s. Skip that number. Nothing in the 50s. Leave the right side blank. There's no data points. 60s. I have 60 Algeria and 63 Syria, 63 Tunisia. So we're going to put a 0. Sorry, not in the 5. And then 3 for 63, and then 3 for 63. If there's a repeat number, you put 2 leaves. It's not like you kind of hide one because you've already taken care of the 63, even though it appears more than once. Put down both 3s. That tells people that there's more than one data value with that number. 70s. We have 70. Let's cross out our 60s first. Okay, 70. I'm looking at 70 Saudi Arabia, 71 Iran, Libya, 71, 78 Turkey. So I'm going to have 0, 1, 1, 8. So 70, 71, 78. So 2 71s and 78 on this list. All right, 80s. I got 86, 82, 85, and that's it. So I'm going to have 2, 5, 6. That's for 82, 85, and 86. And then 9, I have 2 99s actually. So Kazakhstan, and then we said Uzbekistan in the beginning. So 2 9s here. So when you line up the data point values like that, the leaves, it makes it easier to see the mounds, if you will, of the data points. This is kind of, this area here has the majority of the data, between 60 and 99% of the literacy rates for the females. So describe what you see. I'm going to put down that there's a large amount of data or a large amount of values between 60 and 99. So you might say to someone, the majority of these countries have literacy rates between 60 and 99%. That could be a statement that is truthful. Down here, we could say there is a smaller cluster outside the majority of the data. And in terms of the actual cluster, it's pretty small, but it's kind of centralized around that 30s, 20 to 40s mark. It might be worth asking, what do we know about these 4 countries? 29, what was that? That was Yemen, 31, 38, Bangladesh, 38, where's that at? Morocco. Do those countries have anything in common? That's what statistics allows us to do. You look at this data set, it doesn't give you any right answers, but allows you to ask those questions like, what else is going on here? These 4 countries have a different literacy rate, much different than the rest of the countries in this list. What's the difference about these, with these 4 countries? And that's the big idea with statistics. You find data, you ask better questions, you find more data, and so on. And this is your stem and leaf plot, or your stem plot, we'll call it. Moving on to different types of things with stem plots. There's a type of stem plot called the back-to-back stem plot. This is really good for comparing 2 sets of data side by side. So comparing 2 sets of data side by side. Kind of akin to a teacher putting a table and a graph on the same paper, so where you don't have to flip a paper over back and forth. If you put the data set right next to each other, it's so much easier to compare across the 2 data sets. In this case, we actually took the some of the data values from the females and males from the first table up front here. We put them on a back-to-back stem plot to kind of show you what's going on here, we have kind of different distributions for the males and the females. While they're both kind of trending, a lot of the data values point towards the the upper end of it. There's very few males with low literacy rate, or countries with low male literacy rates. If you look down here, for example, there's nothing between 20 and 40% literacy rate. The lowest is half, 50% of the population. While you have females in certain, those 4 countries we talked about earlier, what's kind of going on there? Why are those literacy rates so low for females in those countries? It's a better question to ask. A statement could be males in this country, or sorry, in these countries tend to have higher literacy rates. And that's kind of the bare bones statement about the data set. Now, but again, we talked about this. Why do they have better literacy rates in these countries? Then you start looking at some research, maybe taking some more data, some observational studies, whatever the statistician feels like doing at that moment. The other item we've put on here is what's called splitting stems. And this happens because you have a lot of data in one stem, and it kind of overpowers the rest of the data. So what you do is you take a stem and you cut it into 2. And that makes it a little bit more manageable, comparable to the rest of the data here. So in this case, let's write down a couple sentences here. We're going to make sure each stem is assigned an equal number of possible leaf digits. For example, So for example, the first 2 stems here, if you look at 0 and 1, I'll try and highlight them for you here. You would usually see that as 1 stem, but this is split up into 2 now because there's so much data condensed in those 2 stems. So if you were to put it as into 1 stem, it's hard to look at with all that data. So we gave it 2 stems, the first stem being 0 to 4 and as the leaves, and then the second stem 5 to 9 are the leaves. Kind of gives us an easier look at the data as a whole, rather than if you made this only 4 stems instead of 8, it's really hard to see what's going on here. So this helps with getting a more detailed look at the overcrowded stem. Stems 0 and 1 are split to give a better look at the distribution. So if things are overcrowded or just too much going on, we like to split the stems. Another thing we like to do is called trimming. Trimming is similar to what you've learned already in your math classes. It's when observed values have many digits, we can remove the last digit or digits and place units on our stem plot. In math, we call this truncating. So this is a different thing from rounding. Rounding, we have rules for up and down. Truncating, essentially you're just chopping off a bunch of information to the certain data point. So, if we had $18,643, we could make that 18,000. Some of you might say, well, that's rounding down. Well, actually, it's not. If we were rounding in the nearest tenth or thousandths place, it would be 19,000. But we're just going to truncate here. We're not going to do rounding, and it's just chopping off information. So it's a little bit different mindset than rounding. So think about that when you're doing trimming. Dot plots are the second type we're going to talk about here. This is simply a number line, and you place dots where the data values are, and you stack dots when there's more than one data or data value showing up in the data set. So if you look at the dot plot given here, sepal length in centimeters. The middle column here looks at 5 centimeters. You got 1, 2, 3, 4, 5. Looks like eight dots, and that looks like it's going to have 8 separate data points with the same exact 5.0 centimeter length. So, a couple things here. Each dot needs to be the same size. Each dot needs to be the same size. This is for obvious reasons. People will take advantage of it if they're not the same size. We could, change dots for data values that we don't want people to see. So we might try and hide them within the graph and still, say that they're there. They have to be equally spaced too. Again, for the obvious reason that someone will try and take advantage of that. Got to keep all the dot plots fair for people looking at them. And then lastly, you need a number line underneath. Without the number line, you can't really tell what the data point is representing. You can get a good idea of the shape of the graph by looking at just the dots, but the number line really gives us, like where's the center, how far is it spread out, and so on. Next question. If you were to make this into a stem plot, then what would the stems be? What should a stem plot be used, and when should a dot plot be used? So this is a good question because some students don't really get when to use what. But if you look at these numbers here, a lot of them are going to be, these in between 5 and 5.5. Could be 5.1. Could be 5.2. It becomes more and more difficult when you have those smaller numbers in terms of using a stem plot, whether a dot plot might be better. So a couple of things with this question. First, stems would be 4 and 5. 2 stems. Now we could split those 2 stems, but then you only have 4 stems. And that's a hard way to look at the data. So only having 2 stems, only having 2 or 4 stems, kind of crowds the data, crowds the plot. Makes it difficult to use. Second thing I would say, dot plots are simply better at accommodating larger data sets. I put dots plots. Let's back that up here. Dot plots are better at accommodating larger data sets. So each of these types of plots has their place. If you have a substantially large data set, just skip the stem plot. It's not really going to work out for you. Also, if you have a short amount of stems, if you only can produce 2 or 4 stems, it's going to be hard to look at the data as well. If you need a more detailed look, go ahead and use a dot plot. Doesn't mean you can't use a stem plot. There are certain situations where you can, especially if you have 2 things you want to compare, 2 data sets, like this back-to-back stem plot is a really good way to look at 2 things at once right next to each other. Otherwise, just go ahead and use a dot plot. All right. Moving on. A couple more I can statements. I can describe the overall pattern, that's shape, center, and spread of a distribution, and identify outliers or departures from the pattern. The shape, center, spread is going to be a big question that's going to be asked every time you look at a graph in statistics. And it's not just for this chapter, it's going to be for the entire year. Shape, center, spread. You're going to be saying it in your sleep. It's something you're always going to be looking at. It's akin to in Algebra 1 where we did domain, range, and then intervals every single time, no matter what the graph was. It's going to be the exact same thing here. Second, identify the shape of a distribution from a graph as roughly symmetric or skewed. So roughly, what's the difference between roughly symmetric or skewed? We're going to talk about that as well. So types of numerical displays. We talked about stem plots already and dot plots. There's some more we didn't talk about yet. Maybe a review for you. Histograms and box plots. Histograms and box plots. Okay, describing numerical data. You're going to look at the shape. You're going to look at the center and then spread. And like I said, always think of these three things when looking at a graph. Your mindset should be, when you first look at a graph, what's the shape, center, spread, and then we'll do whatever we're talking about. The first thing you do is shape, center, spread, though, every single time. Get you really looking at the what kind of data set it is, because the shape, center, spread tell you quite a bit of information right up front, and then you can start going into some more deeper questions after that. But the first thing, shape, center, spread. We're going to look at the outliers as well. These are points / values far away from the majority of the data. So things that just don't look like they fit in, that's going to be an outlier. I'll keep an eye out for those. All right, so I have a bunch of different graphs here on this paper. I got some stem plots down here. I got some box plots. We haven't talked about box plots yet, though, but we will. Just get an idea of what the shape, center, spread is going to look like through the different types of plots. So first, shape. That's the first thing we're going to talk about is shape. Let's change up the color here. Let's do red. Words to use. Symmetric. Like in geometry, kind of like a mirror image. That's what you're looking for with symmetric. The next thing you look for, skewed left or skewed right. Which is it, if at all? It cannot be symmetric and, sorry, I wrote skewed left twice. Let's back that up. Skewed left or skewed right. These can't be this. These are mutually exclusive. Either it's going to be symmetric or skewed. It can't be both. It's also possible for these to be bimodal, meaning that there's two essentially bumps here. The most common value happens twice in two different spots, and then uniform. Uniform, all. Very obvious what that looks like in the graph. In terms of skewed left, skewed right, when you're looking at skew, the name of the skew is where the tail is at. So let's turn our direction down to these two graphs. If you'll notice that one tail goes off to the left here, and then one goes off to the right here. This is going to be your skew left, or skewed left. So the majority of the data is off to the right, but we have some outliers here, that kind of pull the data to the left. And this is going to be skewed right. It's the exact mirror image of it. You have to keep track of what skewed left looks like and skewed right. Some students do confuse the two because you're going to want to say well, it's kind of being the shape is pushed to the left, but it looks like it's pushed or pulled to the right. Memorize this picture here. Think about taking your hand and kind of pulling the curve to the left. That's skewing it, and kind of pulling out, kind of like a Play-Doh when you thin out a piece and kind of skew it that way. Same with the right as well. The idea here is though, when you have this tail, that's where those outliers are at. They're kind of pulling that data data set to the right or to the left, respectively. Let's look over here. Box plots, if you look here and here, serious skewness going on. These big, long distances here, that means there's lack of data there. It's very far spaced out when you have a lot of stuff crammed in here, from here to here. And then you have this drawn out right here. Okay, that's gonna be kind of like this up here, but reversed. I said that one right there, skewed to the right. A lot of data crammed to the left, and a lot of data spread out to the right. This other starred one, skewed left. Again, this data right there, spread out quite a bit. This box plot down here, it's kind of facing vertically. If we're going from increasing to decreasing, this space here, skewed right. The bigger numbers are kind of spread out. And then they show you the two kinds of skew right here with stem plots, if you'll notice. Big chunk of the data here for right skewed, right in the beginning, and then left skewed, big chunk of the data with the bigger numbers, and then a little bit of data here. Where I'm pointing these arrows to in the stem plots, that's where that big long line is in the box plot, and the big, the big tails up there in the curves. All right, let's move on from the skewed, and let's look for bimodal. That's somewhat easy to look for. It's just, this first one. This graph's got two major curves, both at the same height, and that prefix bi means two, and the modal stands for mode, so it's got two modes here, bimodal. It's also symmetric in a way, because both curves are kind of repeated. But bimodal would be more appropriate for this graph here. Uniform. A uniform graph looks like this. The horizontal line represents all the different data values that appear the same amount of times, and it creates that rectangular shape in the graph. This one here is going to be your symmetric. Eventually we'll talk about how it's this actually graph is called normal. That should be review for you, but we'll talk about more of that later. But this is definitely symmetric. More likely this, more like the stem plot here, symmetric data, very similar to the symmetric curve up top, right there. Moving on to center, mean, median, and we'll talk about mode again real quick. Mean, the mean of a data set is what's also called, most likely the average. We're going to use some notation here because mean and median are review of old things. The mean is going to be the sum of all the data values and divided by the number of data values that actually exist. So we're going to write this mean as what's called x bar. Whenever you see x bar, you're going to think that's the mean. It's going to be equal to the fraction. Underneath we said it's the number of items in a data set. Lowercase n. Lowercase n will be number of data values in data set. That lowercase n will always be number of data values in set. You're going to divide the sum, sigma notation here, of each individual data value. Sigma notation just means we're going to sum all the different x sub i's, so every one of the data values. So that's just x1 means any data value. And then the sigma, remember, means sum. Just some shorthand notation for that. But the big thing here, you got to remember x bar. Whenever you see that, it's going to be mean. Median, much like the road, it's the middle number of the data set. or more specifically, the value that splits the data set in half, into two halves. Mean versus median. So when to use what? Many people don't know when to use them, or if there's a difference between them. There will most likely be a difference in a data set. If the distribution is symmetric, however, the mean and median are close to equal. If you have a symmetric data set, the one looks like this up here, this on the right there, top right, the mean and median are probably going to be somewhat the same or exactly the same. In a skewed distribution, however, that's where things change. So in a skewed distribution, I'm going to shorthand distribution, the mean is further out along the tail than the median. So I'll try and visualize this for you with a picture. Let's say we have a curve and it's skewed right. Okay. So what happens here is that these outliers on the end, because you're taking the mean takes in every single data value, those outliers affect the mean, and they draw the mean towards the skew. They draw the mean towards the skew. Now, why is this a bad thing? It's a bad thing because if you have any outliers that are really bad, your mean will not represent the actual data set average. So that's one of the big weaknesses with the mean. So we call this the mean. It's sensitive to outliers in that it goes towards the tail of the skewed distribution. For this reason, we say the mean is not a resistant measure of center. It's not a resistant measure of center. So that's the big weakness with a mean. If it's symmetric, you don't have to worry about it, but a lot of the data sets we deal with aren't symmetric, so the mean could be seriously affected by outliers. The mean and the median are used in often a matter of judgment. In general, we use the mean for symmetric distribution and the median for skewed distributions. So let's talk about the mean and median real quick. The median, the big strength is it is resistant to outliers. The problem with the median is that if you have some outliers that are actually really important, the median is not going to reflect that. If I were to swap out two outliers, make one really, really big and then one not so big, the median doesn't change at all. So if you're just using the median there, you would have no idea that the outlier changed. And that's the big weakness with the median. So the mean and median are used hand in hand depending on the distribution. One of the weaknesses of one of the measure center is the strength of the other one. So those are your measures of center with quantitative data. The mode has its place with quantitative data, but it's not a really good measure of center. It's more for categorical, favorite color, favorite sports team, and so on. All right, so we've done shape, we've done center. Now we're going to look at spread. So how far is the data spread out? That's the variability. How different are the values? Are they really different? Are they pretty close to being the same? That's what spread asks or answers. So how different are the values for a variable? Okay. Range. Again, this is very basic. Spread largest minus the smallest. Or more specifically, it's the largest value minus the smallest value. It's worth noting that if you have an outlier, your outlier will be the largest or smallest value, which makes the range not resistant. Makes your range not resistant. It is affected by outliers, you could say. That's what that means. Not resistant, affected by outliers. So we use range, We also use interquartile range. This is a review of a topic we talked about with box plots in previous years. It's your quartile 3 minus your quartile 1. It's the middle 50% of data. So that middle 50% of data, that middle chunk, how big is it? Is it really far apart? Is it pretty close together? That's what that interquartile range does for you. If you're going to talk about the median or the order-based ranges, the range, interquartile range, there's two other ones that actually involve certain equations that uses the mean. So the first two there, range, interquartile range, most talk about when you talk about the median. If you're using the mean for a data set, you can also use variance and standard deviation. Variance and standard deviation are kind of difficult to actually word and explain because they use an equation. But let's try and define and talk about the basics right now because we're going to go into more details in 1.3. So variance is the square of standard deviation. So we're going to call variance S squared. So in terms of the mean, it's how far out the spread is. So we're talking about a mean-based spread measurement. So it's how far out the spread is. And we just said standard deviation, S is going to be equal to the square root of the variance. They're directly related. They do a little bit, different stuff though. Standard deviation, it's a way of looking at how far out or how far our observations are from the mean. So you're not comparing them to the median like other ranges. It's the most popular measure of spread. It's derived from the formula for variance. And it should only be used when the mean is an appropriate measure of center. That's because the standard deviation is not resistant. It's affected by outliers as well. So if you have a bunch of outliers or it's a skewed data set, you can't really use variance and standard deviation very well. It doesn't have to be perfectly symmetrical, but it should be somewhat symmetrical or just not skewed, way out of whack. If you have a value, S equals 0, that only happens when all the data values are the same. So if you have 10 heights of people and they're all 6 feet, your standard deviation is 0 because nothing varies from 6 feet. They're all the same. Otherwise, S is always positive. If it's not S equals 0, it's S greater than 0. You can't really have a negative standard deviation. In terms of the definition, doesn't make a whole lot of sense because you're square rooting a number and you can't get a negative root necessarily without considering the positive root as well. Also, you're trying to figure out how much it's spread out. So in terms of, there's no direction with spread. Just put a little note here for yourself. There's going to be more details about the equation, the derivation in 1.3. So if you're interested in how this actually works and how to derive it, we'll get there. Just want a brief overview right now. All right, a couple more I can statements. I can make and interpret histograms of quantitative data. I can compare distributions of quantitative data using dot plots, stem plots, or histograms. Histograms we haven't talked about yet, but this should be, again, mostly review in lower grades. They take a while to do in terms of by hand. So we're going to go ahead and show you how to use the calculator to actually input the data and then create your own histogram. So histograms, the users display large sets of quantitative data. They break the range of values into classes or bins. That way you're not making a bunch of different bars. You can kind of group things into a class. Classes display the count or the percent. So that's we're talking about count. That would be just frequency. Percent, remember, is relative frequency. Of observations that fall into each class. We can have a various number of classes, but each class should have an equal width. Again, this is so that people can't take advantage of that because they might make a class really big or really small to make their graph look a certain way to sell a product or misinform certain people and so on. So to be ethical, you got to have your histogram have the same equal width for each class. Histogram versus bar graph. Let's make 2 columns here. We'll put histogram here, and then we're going to put bar graph over here. The whole reason we do this is because they look so similar that people confuse them all the time. Okay? First of all, histogram is a single quantitative variable. Single quantitative variable. A bar graph is the distribution of qualitative variables usually. Second, horizontal axis for a histogram is a number line. For a bar graph, the horizontal axis has categories. Lastly, because the horizontal axis for a histogram is a number line, there are no spaces between bars. This is the number one way to figure out if you're looking at a histogram or bar graph. Do you have spaces between bars? If there are no spaces, that means you have a continuous number line. It's a histogram. If you have spaces, then you're looking at a bar graph. Now, I want to just enter a little starred statement here because it is possible to have empty space in a histogram when you have a class with 0 frequency. Okay. Then there's going to be an empty space. Otherwise, you're going to have bars that are touching each other. All right, so we're looking at this data set for our histogram. Obviously, you got a ton of data here. You're not going to want to do like we used to by hand. You're going to make your own classes. You're going to do all the counting. It's a lot of work, and we don't have much time in this class. So what we're going to do is we're going to take advantage of our technology here, and we're going to use our calculators to do that for us. So, kind of write down directions for your TI-83 or 84, your calc directions to do this for you. First of all, stat button. Find it, hit it. Then you're going to hit edit. That brings you to a list, a bunch of lists. We're going to focus on L1. You're going to type all this data into L1. So type data into L1. If you have old data in there, press clear. So I'll put a star here. Press clear for old data. But be careful. Do not hit delete. This is because it's kind of difficult to get the list back. A lot of students accidentally delete L1 entirely. You don't want to do that. Okay. So once you type that in, you can go to the stat plot button. It's the second y equals button. And you're going to turn on plot 1. And you're going to choose histogram. The histogram under type. And then your X list is L1, what you just typed into. And then the big thing here is, what's nice, the calculator zooms in for you to where you want to go, right where the data is centered at. So you press the zoom button after you press graph, and then 9. That's your zoom stat. the calculator just knows where to go to find to kind of center the data into one spot. Now, I'm going to draw a visualization of what that should look like for you. It's going to take a little bit of time. But also, when it says the directions say draw the histogram below and comment on the distribution, we're talking about the shape, center, and spread there afterwards. So I'm going to draw my axes real quick, briefly. We have counts from 0 to 20, so I'm going to go 0 here. Let's do 5, 10, 15, and then top will be 20. Try and keep this good. We have 1, 2, 3, 4, 5, 6, 7, 8 classes on our calculator. So I'm going to draw just 7 dash marks here. 1, 2, 3, sorry, 8, 4, 5, 6, 7, 8. And the important thing here, the class width, you got to kind of write this very small. So I'm going to try and zoom in the best I can. The first class was 82 to 90. Let's see if I can make this thinner. There we go. 82 to 90, 91 to 99, 100 to 108, 109 to 117, 118 to 126, and then 127 to 135, 136 to 144, and then 145 to 153. Okay, so those are your 8 classes. They're going to have different heights of the bars. So let's go back to this thickness here. The first height, we had 3, so it's going to be around there. And the second, 9199, had the exact same height. The third class, 108 to 100 to 108, had a height of 11. So it looks like that. And again, this is a rough sketch, so if it doesn't look perfect, that's fine. I'm just going to get an idea. 119 or 109 to 117 is going to be 19. And then 118 to 126 is 10. So a little bit lower. And then we had 9 for 127 to 135. And then 6 for, or 5 for 136 to 144. And then 145 to 153 is going to be just 1 count. Okay. So this is a rough sketch. If you're doing a final draft example, this is going to look a lot nicer. You're going to use a ruler, some graph paper. This is just to get an idea of what the sketch, the graph looks like. As far as the comment on distribution, let's make a little note here. I'm going to change colors. The distribution comments. First of all, it's almost symmetric. I wouldn't call it skewed at all. There's no big outliers. There's no big gaps in the data set. Almost symmetric, we'll say. The center. So that was shape. Now we're going into center. The center is in 109 to 117. And how we know for sure, it's actually not that hard to do. If you think about how many data values there actually are, we have a 6 by 10 array of numbers. That's 60 numbers. The halfway point would be 30 and 31. Halfway would be 30. So what you want to do there is you're going to count the bars here and then see where the 30th data value would fall. You're looking at 3. This is 3 here, 3 here. That's 6. The next one was 11. So far that's going to be 17 so far. This height here is 19. So once you get there, you pass the 30th data value somewhere in there. I don't know where it's at. Okay, I don't know exactly where the median is or the center. It's somewhere in there though. Okay, and doesn't appear to be any outliers. To have outliers. That's the center. Spread. We didn't talk about the range really. Say the range. The largest number, I think we found it to be, if I'm looking at this table correctly, 145 maybe? Do you have any 150s? So 145 minus the smallest number, 89 could be the smallest number maybe? I'm not seeing any other numbers in the 80s. 81, sorry. 81 could be the smallest number. Okay, double check all the columns. Looks like 81. You subtract those two numbers, you get 64. That's the range of values, shape, center, spread. Always be doing that on a graph. Okay. This just says comment on the distribution. It doesn't say make any conclusions. I mean, it says the table's IQ scores of 60 fifth graders chosen at random from one school. It doesn't say make a comment on the IQ scores. It simply just says what's the distribution, what's it look like. Don't draw any conclusions yet. That'll be further in the future. Just to recap what we did, this lesson was all about how to display quantitative data, histograms, dot plots, stem plots, all the different types that are possible. You have to know all of these individually. Histograms, it's a little bit easier with the calculator help. Stem plots and dot plots, you usually don't need a calculator to do that because it's a smaller data set. There's less calculation going on there. But you definitely need to know shape, center, spread over and over and over again. Looking over this page here, making sure you understand those words, how to use them, what do they look like on a box plot or even a stem plot or just a regular old graph curve. Talk about the center, mean, median, that's review. We did some new notation up here. Make sure you know your summative notation or sigma notation. We defined n, we defined x bar, and we also talked about variance and standard deviation. More details to come in section 1.3. We'll actually talk about how it's derived moving forward. And that's it for section 1.2.